All right, welcome back, everyone. We are going to move to our next panel, which is Robotics and Autonomy, the Big Picture. And this panel will be fully virtual, so we'll be switching over to that in our room momentarily. The moderator for the panel is Dr. Lethia Jackson from Bowie State University. Dr. Lethia Jackson is a full professor and founding chair of the Department of Technology and Security. Dr. Jackson holds a terminal degree in computer science from the George Washington University, a master's degree in computer science from North Carolina State University, and a bachelor's of science degree in computer science from North Carolina Agricultural and Technical University. I am going to pass this over to you, Dr. Jackson, if that's all right. And we are very much looking forward to the next panel. Thank you so much. And you are muted. Sorry about that.
Hello again, everyone. The goal of this panel is to bring together those with experience in the high-level systems as it concerns operating infrastructure elements autonomously. Questions will include not only how the physical components need to work together, but AI, machine learning, and cybersecurity play into the big picture concerns. Another goal of this panel is to learn more about how to engage students in our work and to communicate with different subdisciplines and sectors with different backgrounds. So let's welcome our three expert panelists today. We have Mr. A.J. Jimmer, the Chief Technology Officer at Lunar Outpost. Lunar Outpost is an advanced technology company with a focus on developing technologies that have both Earth and space applications. They plan on expanding space industry and are currently using their technical expertise to solve a variety of technology-based challenges. Next, we have Mr. Stephen Hart, Senior Scientist at TRAClabs, a private company that works in the military, defense, and space industry, specializing in aerospace, automation, defense, electric procedures, robotics, and software development. Our third panelist is Dr. Hazel Edwards, Chair and Professor of the Department of Architecture at Howard University. Howard University is a private, federally chartered, historically Black R2 research university. Dr. Edwards leads the architecture design for habitats optimized for missions of exploration, which is called HOME, Space Technology Research Institute for Deep Space Habitat Design. And she's one of 2 Space Technology Research Institutes selected by NASA in 2019. So at this time, thank you guys for being present. We're going to ask some questions, and I'm going to start with Mr. Jimmer, and then after that, anybody is welcome to continue on with the conversation. So Mr. Jimmer, what do you see as the biggest challenge, technical, administrative, budgetary, etc., for deploying, operating, and maintaining autonomous systems and robotics on the moon?
Well, I'm speaking from the perspective of a commercial company that's looking to, fly repeated hardware deliveries to the lunar surface and provide mobility for our customers. So one of the biggest challenges that we face, of course, is cost and justifying that there is a customer demand and customer need for our mobility services. For the last few years, there has been something of a chicken and an egg problem with, commercial companies saying, okay, well, we're willing to invest a little bit of internal funds into developing these capabilities, but to our customers, can you pledge that you're willing to pay for them? And the customers say, well, yes, but we would like to see the capabilities available and demonstrated first. So we believe that we're already in the early stages of overcoming that. We have our first mission next December, and that is with a commercial customer. To reach that point, we did have to invest our internal funds into the development of a platform that would demonstrate that we had the capabilities and the COTS components to meet the needs of this customer. So that has been a big challenge for, I think, a number of commercial space startups in the recent past.
Mr. Jimmer, while you're here, I'm going to ask, do you have any slides that you would like to share?
I do. I prepared just a couple of slides.
Okay.
Oh, here we go. So that's just my introduction slide. As I said, I'm the Chief Technical Officer of Lunar Outpost, headquartered in Golden, Colorado. And so the problem that we set out to solve was that historically, planetary rovers are expensive. They have long development timelines. and they're fairly crowded in terms of their instrument payloads. Some points of comparison would be the Perseverance rover with a cost of $2.75 billion, which took over 100 days for just the full system checkouts before the science operations really even began. And it's a host to 7 primary instruments, all of which have, complementary but also competing goals and concepts of operations. Similarly, looking at the moon, the Viper life cycle cost is right now pegged at about $433 million with 4 primary instruments. And Viper requires a dedicated lander. So if we as a commercial company had requested an entire lander to ourselves again, that would have made it much more competitive and raised the cost of access to the lunar surface. Next slide, please. And so we addressed this by developing a relatively small, low mass, 10 to 20 kilogram commercial off-the-shelf lunar rover platform, which we call MAP, the Mobile Autonomous Prospecting Platform. And we've marketed this to a variety of different customers who fall broadly into 2 categories: commercial customers, such as Nokia, who will be providing the payload for our first mission next December, but also science and research customers. So the rover on the right is supporting APL's Lunar Vertex mission in late 2023 or early 2024. And both of these customers benefit from some of the autonomous capabilities that we've developed here at Lunar Outpost. Next slide, please. So a concrete example of how autonomy has been benefiting our customers is for our first mission, which is a communications-focused payload. We needed to figure out a drive path at our landing site that optimized for a number of different variables, but primarily for remaining in an area that is illuminated by the sun at the South Pole, while also remaining within communications range. And so the plot on the right there, figure 2, shows the RF propagation at our landing site, with the yellow area being high communications throughputs and the blue area being low, although not zero communications. And so you can see from approximately 1/3 to 2/3 of our red path there, we are outside of the area of optimal communications. And the purpose of that is to remain within optimally sunlit areas. However, because our autonomous waypoint driving algorithms actually require lower communications throughput than strict teleoperation, we can apply waypoints in that area of low communications and navigate through that area while remaining in sunlight, and then return to an area of high communications there for about the last third of the mission. And so, speaking to the title of this panel, Robotics and Autonomy in the Big Picture, this sort of describes a case, a really application-focused case, where autonomy is solving a very near-term customer problem. I believe that is my last slide.
Okay, my next question is for Dr. Edwards. How do you frame these ambiguous questions like, how do you design, build, and operate a habitat in space or the lunar surface in a way that is both engaging and tenable to students, especially at the undergraduate level?
Thank you, Dr. Jackson. And first, I just want to clarify that the Howard team is one of 7 institutions that comprise the home STRI. So the home STRI is one of 2 space technology research institutes funded by NASA in not Howard being the whole one. So we are we are different than the other 6 institutions in that we are strictly architecture. And so for us, when we began this exercise in 2019, it was trying to, and the students again are all architecture students. They were in their 3rd year of a 5-year program. And so our main research question was, or our starting point, I should say, is that, what does it mean to dwell in a terrestrial condition, and how can this translate to living in zero or partial gravity in a scenario like that? And so, we had removed all of the things that the other institutions are addressing in terms of robotics and autonomy. We began with, okay, all of the students live in a dorm. what are the things that in terms of having a lot of people, high density housing, how can we translate those things into what could ultimately be a part of a space habitat? And so the team quickly moved into 3 areas: territoriality, functionality, and mental health, which later in year 2 translated to multifunctionality. Mental health was still a very, very strong component, and then lighting. And so they looked at things. One of the students was working specifically on biomimicry and biophilia, and had an interesting series of exercises where she, for example, took a cross-section of a cactus plant and looked at how circulation and other aspects of the cactus could be translated into what we were understanding to be potential for the space habitat. And we've used the design thinking process to really understand this exercise and try to I would say catch up, because we're starting from just a purely earthbound perspective. What we know is, as designers of buildings, how does that then translate into something that's maybe only going to have a crew of 4 to 6 people, and robots, there the majority of the time.
Do you have any slides to share, Dr. Edwards?
No, I'm not
Okay.
going to share them.
Okay, thank you. Mr. Hart, how do you foster communication and address a large-scale design problem with a team that includes people with engineering, architecture, business, or science backgrounds? Can you offer advice to make sure we can all learn to speak the same language?
Yeah, for sure. That is definitely one of the bigger problems that we always have to address. We're mainly a small group of researchers, mostly PhD level with some staff programming and mostly software based, but we're having to communicate what we're doing in terms of cutting edge state-of-the-art research to our business people, so that we can communicate how to push forward and develop that technology, but then also working with the larger staffs, most specifically with the larger NASA teams that we have to that we work with and have to communicate well with. And what a lot of our research and efforts have been focused on is trying to find good standards for software and communications, such that there's a common footing and a common grounding that we can all work with. We're a big proponent of the robot operating system ROS framework, which I assume a lot of people are familiar with. That has helped us in a number of ways. One, because by working with NASA to develop ROS-based standards for their robotic systems, that's allowed us to push some of the research and easily integrate with the robots that we're working with, things like Valkyrie or Astrobe. But it's also been very useful for bringing on new talent and working with our university partners and interns and students that we have, because it avoids a lot of the up to speed time. We can easily plug a lot of these people into the work we're doing and quickly make progress. So yeah, I think standardization, and the more that the larger community can adopt standards, both in terms of communication protocols, but also in terms of the specific data that's actually being transmitted, and focusing on and appreciating that the integration effort, no matter how well people try to anticipate it ahead of time, is always going to be arguably 90% of the problem. So focusing on integration and developing tools that make integration easier and transparent are definitely things that we try to encourage.
Thank you. Do you have any slides you wish to share?
I do.
Okay.
Don't see them on the screen. Great. Yeah, so we're, like I said, we're a small company. We're located in Webster, Texas, which is basically Houston, right down the street from Johnson Space Center. You can go to the next slide. We started in the mid to late 90s. I only came on about 7 years ago, but the company has been around and largely working with JSC and Ames Research in various robotics projects in their advanced humanoid and research groups. So we have a long history, especially around things like Robonaut and Robonaut 2. We were a participant in the DARPA Robotics Challenge. We were the only small business to finish in the top 10 back in 2015. We were one of the teams that just did the software and used the Boston Dynamics Atlas robot. And around that time, we sort of was a culmination of when we brought together a lot of our NASA-based research, largely funded through SBIR and STTR projects, and the DARPA Challenge to try to come up with a standard application, ROS-based application framework that we could use in our ongoing research. We call that Craftsman, and we've since used that on robots like Valkyrie and also deployed it in industry, specifically automotive manufacturing. And as far as I know, we're the only, we were the first people to deploy a flexible manufacturing ROS-based cell in automotive in the US. So that was really helpful for us to shore up the efficacy of the software outside of the research context and get it out into the field. So next slide. We are largely a SBIR-based company, although we have taken some of the work that we've developed in that context and commercialized it. Specifically, we have an electronic procedure software called Pride. It was developed with NASA, but we've since turned that into a product that we've deployed in thousands of cases for oil and gas and chemical and commercial aerospace. But that's a way for getting the procedures out of the printed out Word documents and binders and putting them into an electronic format where you can actually connect them to your command and telemetry systems and then even automate tasks. We've done a little bit of work hooking that up to a robotic system, so but that's mainly a non-robotic effort. We have a number of ongoing projects right now. Specifically, we're working on a few of them with the NASA Ames team for Isaac and the caretaking applications for Gateway and Astrobe and coordinating Astrobe with other robots. We are working with the Viper team as well, doing some of the perception-based ROS2 framework, as well as some of the ground system software, largely helping out in various places as they need to. I just finished up a recent project that looked at bridging ROS2 with the core flight system software, recognizing that, again, getting back to standardization, lots of people have different standards, right? We want to get on the same page and we want to take advantage of the capabilities and of different systems. And if we have to make things work together, then how do we do that? And ROS and core flight system software is definitely something that I think we should all kind of look at how that stuff fits together. Some other work in terms of deploying our Craftsman software in OSAM and habitat assembly context, and specifically expanding it to better handle coordinating multiple robots, heterogeneous teams of robots to perform things like habitat assembly and OSAM tasks. Next. I think I just have a couple videos. So hopefully they'll play. You can play them both at the same time, if possible. On the top left is the Valkyrie robot. We worked with the JSC team, getting our Craftsman software to help out with some tasks they were doing, specifically funded by DoD actually. And this was a situation where they're trying to get humanoid robots in humanoid environments or human environments to do bomb disposal tasks, right? So the robot has to navigate uncertain and uneven terrain. We worked also with IHMC on this. They provided the control and walking software. But our ROS-based software, as you can see here, allowed us to have the robot do some manipulation tasks in a shared autonomy environment. So some task structures that the operator who's remote and not in the line of sight can actually guide the robot and help with things like perception tasks, and then let the robot take care of some of the specifics. And we're pushing this sort of shared autonomy, human in the loop only occasionally framework to better help longer term flight missions. And that's really the goal here. You can play the next one, the bottom one. This is, I'll end with this one, but this is just another example where we integrated that electronic procedure software with our robotics craftsman software in that caretaking context. And in this situation, we see the procedure being automated on the left. There's the telemetry from the spacecraft on the right. We use our custom simulation for that called BioSim. We can go in and induce faults. And when this happens, say if we induce a fault in the COT system, the procedure can coordinate the activities of multiple robots. And in this case, tells Astrobee to go inspect a vent to see if there might be something in the way. And if Astrobee finds something in the way, the procedure can coordinate a more dexterous robot like Robonaut to actually do something about it. And in this case, the Astrobee finds a sock in front of the vent, and Robonaut, conveniently located close by, can turn around and remove the obstruction of the vent. So just a way of integrating multiple systems together in a way, again, speaking the same language, and but also in a way that humans can understand. So yeah, I'll end with that.
Thank you so much. Those videos are always so great and entertaining to watch. I know I get hooked on Boston Dynamics, which you did help them with that competition. So thank you so much for sharing that. I have a question. Several students are always asking me about the autonomous robotics and how that works. So I want to ask each of you. I want to know your advice for computer technology, computer science, engineering, and the like students about what types of classes, research, or activities that might best prepare them to become involved in a company such as yours for space or lunar exploration. And also Dr. Edwards, as well as what is it that you know from your experience of the students that are actually in your research space. So we'll start with you, Dr. Edwards, and then we'll go to Mr. Jimmer, and then we'll go to Mr. Hart.
Excuse me. I think one of the things that we've learned these past 2.5 years is that our students really have to have a strong math orientation. And so again, our students started this process as juniors, but in the third year in a 5-year program, and we needed them to have completed the math, the physics class, and other computer representation courses, or at least understand the software. So now they're using Grasshopper. They've been using some Autodesk products to help with we haven't quite gotten to animation of the projects, but I think having, and for us, it's also about having a broad perspective so that it's not just about design, but it's, with students who've taken psychology classes, because we keep coming back to mental health being so important in this process of designing for the space habitat.
I think it's my turn. So yeah, I think my advice to students, I have 3 points, 2 of which in my experience, they're already doing very well at. The first would be to keep up to date on the state of the space industry and how autonomy is being applied to solve near-term problems, but also being proposed to solve more futuristic problems. And I think students are very good at that with their use of social media and things of that nature. But I think that brings a lot of benefit to a commercial company just being really well informed on the state of the industry and the scientific community in this area. And another thing we've seen really being done well by students is coming up with creative new ideas, really thinking far out there and finding their inspiration in space and space exploration and the commercial space industry. At a commercial company, we tend to be very focused on the problem at hand and meeting our customers' needs, but it's always good to have that broader view and that really forward-looking perspective, which I think students are particularly good at bringing. And my last piece of advice related to projects would be to seek out projects that do involve actual application and real-world testing of their autonomy. It's pretty common to dive heavily into the simulation environments and things like that. And of course, that's the critical first step. But sometimes making the jump to existing hardware can present some pretty unique challenges. And so experience in assessing those and overcoming those application related challenges is very valuable.
Thank you, Mr. Hart.
Yeah, I'd certainly echo a lot of what everyone's saying, and in particular the balance. I think robotics is interesting because it lies at the intersection of so many fields, and you might get some people with good math and physics background, but software design might not be their strong suit or their background, and vice versa. So I think covering the grounds of math, physics, and software design, and engineering too, if it's going to be more on the hardware side, is important, but certainly then also pursuing internships in industry so that you can see how this stuff gets applied in reality is always eye-opening and really beats everything else, right?
Well, thank you. Dr. Edwards, you mentioned the M word, math. When you say math, what math are you talking about? Are you talking about calculus, calculus 1, calculus 2, calculus 3? I mean, which ones are you talking about?
So our program doesn't require, most of the students who are working on our project have placed into or taken calculus 1, but and so our requirement isn't the same for architecture, the architecture program, as it is for the engineering programs within our college. Yeah.
Well, that sounds great. So I'm going to move into a question I want everybody to answer, which is what can the federal government do to help foster and catalyze the commercial space of the robotics industry, such as development of prototypes, reducing risk, establishing standards, releasing reference data sets, establish test beds, create public-private partnerships. So I want to start with you, Mr. Hart, with that question.
Yeah, I mean, lots of possibilities. I think standardization is certainly really important. I think as, like I said, largely a SBIR company, we're going through the grind a lot, right? It's a very cyclical process, and there's certainly opportunities, and there's some great programs to do extensions off of those that can lead to some longer term funding and support. But as AJ was saying earlier, right, there's this balance of the support that you're getting with the internal funding, and especially with the SBIRs, it can be it can be a grind, right? Just in terms of the cyclical nature, and it's always kind of disappointing when we get through them and it's like, all right, put it on the shelf and hope that maybe someday we can pick it up again. So I think longer term support contracts to push things from the lower SBIR phase 1 level into more extensive prototypes that are encouraged to be integrated directly with NASA systems, for example, would help with some of the longevity and encourage things to have longer life cycles.
I see a lot of agreement among each other. Mr. Jimmer, do you have anything to add to that?
You're muted.
Your mic is off, Mr. Jimmer.
Sorry. Yeah, that was very similar to what my answer to the question was going to be. A number of the suggestions, like releasing reference data sets and creating public-private partnerships, are certainly important. Specifically, I think we would like to see more STMD funded missions with a very specific technology demonstration or development focus. It makes sense that these early missions would focus on answering the open science questions because that feeds into the technology development needs for future missions. But it would be nice to see some more missions funded for explicitly for the goal of developing those future technologies and less closely tied to answering a specific science question.
All right, Dr. Edwards.
I don't really have anything to add except, just kind of going back to the initial contact that I had with the lead for our project, and the interest in including architecture in this exercise or in this STRI was considered very, very important because we would bring a different lens to the project. And so I think being open to different perspectives, having we don't speak the same language, we're coming to find out as engineers do, but we're coming to some agreement about what certain terminology means. But I guess for the federal government to support kind of the non-traditional viewpoints that contribute to ultimately to the design, the end product.
Sounds great. I want to take this time now to open up the floor if there's any questions so that we can ask our specialists. Any thoughts? Do we have any questions? Rachel, you have any questions you want to read? Are there any? Your mic is off.
Looks like they're having some mic battery issues.
This reminds me of my dual modality class. Well, while they're waiting, is there anything that anybody else would like to say on the panel? I just want to know, one last thought is, how much of a crossover do you see between the technologies needed to establish architectural infrastructure on the moon and applications on the Earth? If anybody could take that question. Is there a crossover?
Yeah, I like that question. I think there is quite a bit of crossover. In fact, that was really part of Lunar Outpost business model, is to establish those space to Earth, but also Earth to space technology pathways. So one of our early products was an air quality, or is an air quality monitoring sensor, which was initially developed for a space habitat to monitor for regolith, but found an application here on Earth in pollution monitoring, wildfire mitigation, and things of that nature. And bringing it to robotics and autonomy, that those types of sensors can be deployed using autonomous platforms similar to rovers here on Earth. In some cases, a flying platform like a drone is not optimal, and so surface mobility, a UGV, is better suited to accessing certain areas and providing monitoring. So I really think there are a lot of pathways. Sometimes it takes some creativity to find them, but those technology flows are very important for commercial companies like ours.
Mr. Hart?
Yeah, not too much to add there. I mean, I think, just to reiterate, really trying to get people to come into working on these projects with speaking the same language and having the same sorts of integration tools, so that can be applied in the different classes of systems without having to start from scratch every time. I mean, I think we're at the point, it's 2021, where there's a large body of technology and work that people have been doing for decades that we should take advantage and build upon to get further faster.
Dr. Edwards, you have any comments?
I just wanted to kind of add to what Stephen just said, that, I think that our students, we have 5 students, I guess a total of maybe 9 students, who've been working with us from the beginning. And, we have our resident, what I'll call our resident ISS expert. And he, the students have done really well to start from zero, if you will, in terms of understanding what is required for a space habitat. And so the crossover, I think that was what your question was. I think that they're, again, going to what I said before, we've got to understand, we've got to work together. Architects are looking at things from a different perspective than the engineers, certainly from the computer scientists. And so being able to facilitate that cross-disciplinary interaction, I think, is really important.
Okay, Stephen, Mr. Hart, what role do you see autonomy and robotics playing in sustainable lunar surface activities such as exploration, commercialization, and tourism? Exciting.
Yeah, I mean, I think we're, full autonomy, of course, where we can let the systems go for long periods of time. It just always feels over the horizon. So I think really looking at avenues where we can share the burdens and be able to effectively coordinate, possibly, one person can coordinate a large team of robots if they don't have to do, a lot of work to do that, right? So looking at how to balance and take advantage of what the robots can do themselves well and have higher level directives from the human operators at a lower time rate that can, make sure things are both proceeding as they expect, as well as, direct the attack, the actions of the system. So, let the robots do the motion planning and the sensor processing and that level of things, and provide the sort of raw materials for the people to make the decisions.
Mr. Jimmer?
Yes, so in sustainable lunar surface activities, as I've said, we really focus on providing mobility as a service to customers of all types, but I think that requires consideration of things such as do no harm to other installations and operations. That's what's going to make it sustainable. And so I think all of the actors operating on the lunar surface, especially as activity increases, need to be mindful of their effects on the environment and on other missions and hardware operating nearby in order to maintain that sustainability.
Okay, thank you, Dr. Edwards.
So I think there's some questions in the chat.
Yeah.
I just can't see the chat. Let me see.
Dr. Jackson, I can speak again now. I'm sorry about that.
Okay.
We had a dead mic, so we did get a couple questions from the audience. One
you.
was for AJ Gemmer, which is, as a commercial company, how do you address the community's desire to standardize software frameworks and in general push for open software solutions?
Yeah, I'd say in general, we very much support standardized and open software solutions, to maintain that interoperability and that ability to iterate quickly, take input from a variety of sources and developers, and really, design the next generation and the next missions quickly and cooperatively. Naturally, as a commercial company, there are going to be some areas where we need to do our own proprietary development. But as the question asked about frameworks, we do that. We work within established and standardized frameworks so that even our proprietary solutions are interoperable with some of the other proposed missions and architectures. So as we heard yesterday, there's work on a space-focused version of ROS, which that sounds like really excellent work and something that we fully support.
Should I do another one? All right, I will real quickly. So this is another one for you, AJ. How developed are your larger rovers relative to MAP?
I'll give the short answer here, but I encourage anyone who really wants to dig into the technical details to reach out and we can speak more about it. MAP, the small rover that I showed, is currently at TRL-6. We do have 2 larger rovers in development as well, both of which are at TRL-4. The larger of them has a 300 kilogram total mass.
Okay, and we only have one other live question, which I can go to and then toss it back to Dr. Jackson, if that's okay. And this is once again for AJ. Has the SMD Prism 2 call, where the proposers can't propose a specific rover, presented any challenges to Lunar Outpost's ability to compete? Any advice to STMD?
Oh, that's a really good question. It was interesting when the Prism 2 call came out and I saw that. I would say yes, it does present some challenges, because I think for the instrument suite and payload providers, they're designing to a very notional rover. Some technical specifications were given, but many were left open. I think Lunar Outpost really welcomed the challenge to, comment on the state of the art and, sort of fill in some of those knowledge gaps on what that rover could look like. But given that it did not provide funding, or, the Prism 2 call did not provide specific funding for technical development of that rover, that did make it somewhat less appealing to a commercial company like Lunar Outpost. So I think we would prefer if rovers could be, specific rovers could be proposed to science calls like Prism. But I also agree that there's a need for establishing the customer needs in terms of the payload requirements in order to arrive at the best technological solution for the large rovers. So it was an interesting way of doing it, and I'm really looking forward to seeing what comes out of that process.
Dr. Jackson, a couple more did appear. Are you okay with me reading a couple more, or did you have others that you want to turn back to the rest of the panel?
No, we're free. We're open. Yes,
Okay,
please.
okay. One for Stephen Hart. What are your thoughts about ROS versus flight software frameworks? And in parentheses, CFS, F prime, et cetera.
Yeah. Yeah, I mean, as I mentioned, we actually just finished a phase 1 STTR with APL at Johns Hopkins, looking at how to bridge CFS and ROS2 in particular. You know, we actually didn't have, or me personally, didn't have a lot of flight software and CFS experience before then, so we learned a lot from APL and definitely explored sort of the benefits and limitations of both systems. And you know, I think what we kind of best determined was that they're very complementary, but they're designed for very different purposes. So, you know, while we can consider things like what would ROS2 look like as flight software, I think in the shorter term, you know, it's better to think about how and what roles the different systems and components can use in the larger system. You know, certainly dealing with better scheduling in real time, you know, processes, you know, the strengths of CFS and integrating various flight components. That's something that ROS doesn't have, but the flexibility of the application libraries and the large user community that's associated with ROS really brings to the table a lot of things that might be best used, maybe not in the flight critical or safety critical components, so possibly even on the ground, but you know, even in limited context on the flight hardware itself. But just not in the loop of that sort of safety critical, the safety critical system. So I think there's a lot of work to get to exactly how to bridge these types of systems. And you know, the biggest thing that we found is that while it's relatively straightforward to think about how we can bridge the communication protocols, that's only the first step. And the harder problem is what's the data that's being shared between the two. And when everybody's developing their own standard for that data, it's very hard to get things back and forth. So looking at how to standardize the content of the data as well as the communication is, I think, kind of the big challenge that we need to address in the short term, because I think we're closely getting to the point where we want to have integrated systems that can take advantage of all of the strengths of the different subsystems.
That's interesting because that feeds right into a question that people have been upvoting like crazy, which is, would it be helpful for NASA to release reference/standardized data sets to help autonomy and robotics developers?
So yes.
Yes. Okay. Question done. Others have any comments on that?
I also agree, though I think some of these, the purpose of some of these early science missions is to establish those data sets. So I think we'll be seeing more and higher fidelity public data sets coming very soon.
And then there's one more currently active, which is from Jonathan Mickelson. Are there specific repositories your teams use to distribute open source and resources you develop to improve accessibility? That's to all of you, I think.
Yeah.
It's a challenge for us, you know, for figuring out exactly how to, what to put out there. And you know, being part of the ROS community, we've certainly contributed and worked in that larger community and put out some things that we could consider, you know, not necessarily proprietary, whether that's fixing drivers or things like that. We've released a few open source packages, but it's hard to balance, again, the sort of long-term maintainability and development of that with trying to keep things in a proprietary sense and push forward, you know, the technology. And I don't think we've completely cracked that nugget. As AJ was saying too, like trying to figure out ways that you can have interoperable, like, you know, create a framework and plugins that you might sort of keep close to the chest as the company, but make sure there's maybe base functionality that you can get out there that would benefit the larger system to at least encourage the standardization and integration efforts. And if you can come in and say, hey, we have a fancier version, you know, that's great too. But it's a constant battle, and it's not clear I mean, from our perspective, it's not clear exactly how to do it.
Yeah, I would echo those sentiments. The one thing that I would have to add is that while we don't have sort of a centralized repository or system for sharing open source projects, we do support a lot of student and intern level projects, and those the results are typically available on the respective university websites or program repositories. So that's something that we really support, is sort of bringing the next generation of students into the work that we're doing.
I would love to take since I have the mic, ask a question of Dr. Edwards, if that's okay. And I'm not going to wait for someone to tell me yes, that it is okay. I'm just going to ask. I would like to know if you have any strategies. So especially coming from an architecture department, you know, you mentioned getting to speak the same language. And yesterday we heard that this is really important, that we bring along people with different backgrounds, and that it's not just just speaking between engineers and scientists is difficult, but when we're bringing in architecture students, when we're bringing in people from the health field, from very different disciplines, do you have any advice about how to get people in a large team, in a large and diverse team, speaking the same language, so that we can really communicate and attack this problem from many different directions?
Thank you for that. You know, one of the things that what I was first thinking is that, so we have 5 research thrusts in our group across the 7 universities. And one of the things, we're in research thrust 1, and we're now focused on adaptive architecture. But early on, maybe at the end of year 1, the head of the research thrust basically prepared a glossary. And so a glossary of terms that they use in their capacity that we then attempted to provide our own definition. And so, you know, that helped us to understand, you know, their perspective, the engineers, computer scientists' perspectives on things that we, you know, we either don't consider or we think about differently. And recently, during one of our meetings, we had this, we said something about, one of the students said, our students said circulation, but then the engineer's perspective of circulation was completely different. And so I think having this, this glossary that we could keep going back to, which defines a lot of different terms, from autonomy to, you know, self-reliance, self-sufficiency, is really important. But fundamentally, we're all talking about design, I think, from different perspectives. We're looking at it from a physical, you know, livability perspective, but then design is not unique to architecture, the study of architecture and buildings.
Thank you. And Dr. Jackson, I'm going to pass it back to you to wrap us up, or if you've got anything last. Any last
No,
questions?
I don't have anything really left to say, unless someone else has something, other than thank you so very much for sharing your time and your information and your thought processes with us about this big topic that's moving bigger than we can even think of. Just enjoy all the videos and everything else. And I think it's so much more to come with all the expertise and the students, especially with pulling all the different disciplines together to make these autonomous systems. So I wish you a great day, and I thank you again.
Thank you so much, Dr. Jackson. Thank you so much to our panelists as well.
Yep,
Thank you.
everybody.
Thank you.